Section: Introduction. In this section, we introduce our approach to Next Token Prediction, NTP, which is the core training goal for large language models. We train our model to predict the next token in a given input sequence from our training data, aiming to optimize the model's parameters. Next, we discuss reinforcement learning with verifiable rewards, RLVR. This method uses reinforcement learning to improve specific skills by relying on a labeled dataset of question-answer pairs. For each question-answer pair, our language model generates a response based on the question. We also present the pre-training task of next token reasoning. In this task, we treat the input sequence as context and require the model to produce a reasoning sequence before predicting the next token. This reasoning process can include various patterns like brainstorming and self-correction, allowing the model to understand deeper knowledge rather than just surface-level correlations. For pre-training with reinforcement learning, we employ reinforcement pre-training, RPT. Here, we prompt our language model to generate multiple responses for a given context. Each response includes a reasoning sequence and a prediction. To assess the accuracy of these predictions, we use a reward system based on whether the prediction matches the ground truth completion sequence at valid token boundaries. We utilize the OmniMath dataset for our reinforcement pre-training, which contains numerous competition-level math problems. To enhance training efficiency, we filter out easily predictable tokens using a proxy model that assesses the uncertainty of predictions. Our main model for these experiments is DeepSeek R1 Distill Qwen 14b, chosen for its reasoning capabilities. During training, we set specific parameters, including a learning rate and batch size, and we sample multiple responses for each question. We also implement dynamic sampling to improve efficiency as training progresses. Overall, we aim for a total of 1,000 training steps, with additional details on our prompt templates provided in the appendix. Section Summary. In this section, we describe our approach to training large language models, LLMs, using next token prediction and reinforcement learning with verifiable rewards, RLVR. We introduce a pre-training task that emphasizes next token reasoning through chain-of-thought processes, utilizing the OmniMath dataset to enhance model performance on challenging tokens while implementing a structured training framework. Section: Evaluation of pre-trained models. In this section, we evaluate pre-trained models. After pre-training, we can directly perform next token prediction and reinforcement fine-tuning for specific tasks. We demonstrate that reinforcement pre-training enhances the language modeling and reasoning skills of large language models. For language modeling, our models are well suited to the next token reasoning task. We assess their performance by measuring the accuracy of next token predictions, which helps us understand the scaling properties of reinforcement pre-training. When fine-tuning on downstream tasks, we apply continual reinforcement learning fine-tuning in a pre-train then fine-tune approach. This alignment reduces the gap between pre-training and reinforcement learning objectives during post-training. We check if reinforcement pre-training further boosts performance on final tasks. We evaluate language modeling on a validation set of 200 samples from OmniMath. Using an entropy-based filtering strategy, we classify token positions by difficulty. We calculate the entropy for each position and categorize them as easy, medium, or hard based on specific thresholds. We compare the performance of our model, R1 Distill Qwen 14b, using two methods: standard next token prediction and next token reasoning, which involves generating a thought process before making a prediction. We also include results from Qwen 2.5-14b, the base model for R1 Distill Qwen 14b. Our findings show that RPT-14b consistently outperforms R1 Distill Qwen 14b across all difficulty levels and matches the performance of a larger model, R1 Distill Qwen 32b. This indicates that reinforcement pre-training effectively captures complex reasoning signals in token generation, enhancing the language modeling capabilities of large language models. Next, we explore the scaling properties of reinforcement pre-training. We observe that the loss from next token pre-training on natural language data follows a power law decay related to model size, training tokens, and compute. We analyze the scaling behavior of RPT concerning training, compute, and model this relationship using a power law form. We evaluate next token prediction accuracy at various training steps and convert these into corresponding training compute values. We also consider the impact of data difficulty by filtering validation splits based on entropy thresholds. Our results show that as we increase training compute, the next token prediction accuracy of RPT improves reliably, with high values indicating a good fit to the observed data. To assess if RPT models can be fine-tuned more effectively with reinforcement learning for verifiable reasoning, RLVR, we randomly select questions with verifiable answers from Skywork OR1 for additional training. We use 256 examples for training and 200 for testing, identifying challenging instances with R1 Distill Qwen32B. We set the training and mini-batch sizes to 64 and train for 15 epochs. During evaluation, we limit the maximum number of tokens to 32,000 with a temperature of 0.6. Our results show that the reinforcement pre-trained model achieves a higher upper bound when further trained with RLVR. However, the model's reasoning ability declines when continually trained on the same data using a next token prediction objective, with subsequent RLVR yielding only slow performance improvements. These findings suggest that reinforcement pre-training can effectively transfer enhanced reasoning patterns to final tasks, even with limited data. Section Summary. In this section, we demonstrate that reinforcement pre-training, RPT, enhances the language modeling and reasoning capabilities of large language models, as evidenced by improved next token prediction accuracy across varying difficulty levels. We also find that RPT models can be effectively fine-tuned with reinforcement learning, leading to better performance on downstream tasks compared to traditional next token prediction methods. Section: Zero-shot performance on end tasks. In this section, we evaluate the zero-shot performance of RPT-14B on end tasks. To compare, we also look at the next token prediction abilities of R1 Distill Qwen14B and R1 Distill Qwen32B, as well as the reasoning performance of RPT-14B alongside R1 Distill Qwen14B. Our assessment uses two well-known benchmarks: MMLU Pro, which tests LLM capabilities across various tasks, and SuperGPQA, a large-scale benchmark with graduate-level reasoning questions from 285 fields. For reasoning, we set the maximum token limit to 12,288 and the temperature to 0.8. Following established methods, we use multiple-choice questions for evaluation and report accuracy. As shown in our results, RPT-14B consistently outperforms R1 Distill Qwen14B in both next token prediction and reasoning across all benchmarks. Remarkably, it also exceeds the larger R1 Distill Qwen32B in next token prediction, achieving a 7-point advantage on SuperGPQA and about a 22-point advantage on MMLU Pro. Detailed results for each subject are available in the appendix. Next, we analyze the differences in reasoning patterns between next token reasoning and explicit problem solving. We measure the proportion of model responses that include reasoning keywords, such as break down and alternatively. Our analysis compares the thought processes of R1 Distill Qwen14B for problem solving and RPT-14B for next token reasoning, based on 200 sampled responses from each model. We categorize reasoning patterns into 6 types: transition, reflection, breakdown, hypothesis, divergent thinking, and deduction. Our findings show that RPT-14B's next token reasoning is significantly different from R1 Distill Qwen14B's problem-solving approach, with a 161.8% higher use of the hypothesis pattern and a 26.2% higher use of the deduction pattern. In contrast, problem-solving relies more on the breakdown pattern, indicating that next token reasoning involves a different inferential process than structured problem-solving. We provide an example of reasoning patterns that illustrates a deliberative process rather than simple pattern matching. The model analyzes the broader context, identifies key phrases, and explores multiple plausible continuations, demonstrating a complex reasoning process that aligns with RPT's goal of fostering deeper understanding. We also discuss the scaling paradigms of large language models, which have advanced through two main dimensions: training time compute and test time compute. Training time scaling increases model parameters and data, using next token prediction for pre-training. Test time scaling, on the other hand, extends inference compute to enhance reasoning capabilities. RPT uniquely combines these principles by framing each next token prediction as a reasoning task. Finally, we highlight the role of reinforcement learning, RL, in the post-training phase of large language models. RL from human feedback fine-tunes pre-trained models based on human preferences to improve alignment. Additionally, large-scale RL is used to boost reasoning capabilities. However, we note that the reward system can be exploited by simply repeating target tokens. To counter this, we utilize next token prediction accuracy as a rule-based reward signal to reduce the risk of reward hacking.